Assalamu alaikum wa rahmatullahi wa barakatuhu. Friends, welcome back to my channel. How can we calculate the value of smoothing capacitor in linear power supply? This is a question from my viewer. To understand capacitor value calculation, we need some considerations. For that purpose, it is best way to calculate a complete power supply, to find the exact value for our calculations and to understand different parameters. For example, I need a power supply to drive this RL. This load resistance needs 5 volt, 500 milliampere. To take good value for this calculation, this is our V out, I out, load voltage and load current. 5 volt, we need regulated 5 volt. Current 500 milliampere, that is maximum current. But we will not run the system at this current. We need some spare headroom for our circuit for safety. So we will take 150%. 500 multiply with 1.5 to take 150%. So it is 750 milliampere. In case there is something wrong with the load, the maximum current will be allowed 750 milliampere. Because we are designing linear power supply, for linear regulators, we regulate the voltage. For 5 volt, 750 milliampere, the next higher option is 1 ampere regulator. So 7805, because we need positive 5 volt, positive regulator. So positive 5 volt 7805, it will provide 5 volt 1 ampere when the line regulation 7 volt minimum up to 25 volt. The normal range is considered 7 volt to 20 volt. So this is a good line. So it will provide regulated voltage when at this point the voltage will drop until 7. It will provide 5 volt. Bypass capacitor 0.1 microfarad for input and output at this regulator. 0.1, 7805 center pin ground. As we discussed, 7 volt to 20 volt can be applied here. So our minimum voltage level is 7 volt. Now we need a capacitor here, smoothing capacitor here. What is its value? These capacitors are recommended components for this 7805. So we don't need to calculate these components. We need to check this one. To calculate this capacitor, we need to understand many parameters. The first, that is minimum voltage 7 volt. We will provide some spare headroom in this voltage level, so that in case this capacitor becomes weak, the system will remain working. We will provide 20% extra margin here. 7 plus 7 multiplied by 0.2, 8.4 volt. If you don't want to provide margin here, no problem, we will consider the same 7 volt. If we don't want to add margin, no problem. Okay, for the time being I will use this voltage level. Here I need bridge rectifier. Which type of rectifier we are using? Full wave, half wave, bridge. The best option to use bridge rectifier. At a time, 2 diodes will remain in circuit. If this end is positive, this end is negative. This diode forward bias, negative side here. This diode forward bias, voltage here. When the current will flow, this diode will drop 0.7, this will drop 0.7. 7 volt And if we are not providing any headroom here, spare headroom, 7 volt plus 0.7 for this diode plus 0.7 for this diode. It is 8.4 volt. This is in that condition when we are calculating with tight calculation. If you are providing some extra headroom at that time, 8.4 plus 1.4, it will 9.8 volts. %, headroom, so it will around 10.08 volts. We will consider 10 volt. We need 10 volt peak here, top level here. When this rectifier will rectify, we need 10 volt here, that are peak voltage. 10 volts, take its RMS value 7 volt. If we have any transformer which is providing 7 volt, that transformer can fulfill the requirement of this regulator. But now, this is transformer. It is ratio based transformer. We need 7 volt. When we are considering the voltage value, we need to take care that it is not a regulated source. If the line is dropped, this voltage will drop. If line has swelling, the voltage will increase. We need 7 volt at dropped line voltage. Standard voltage 220 volt, minus 20% line drop. 220 minus 220 multiply with 0.2, 176 volt. This transformer will provide 7 volt when the line is dropped. Because if we will consider as 220 volt, this voltage will drop. At that time, this circuit will stop working. We must consider the line drop. Now, 7 volts plus 7 multiplied by 0.2, 8.4 volt. We can say at 220 volt, this transformer will 8.4 volt RMS. What is the current? We are considering here 1 ampere because this regulator will provide 1 ampere maximum. So we will provide 1 ampere here. Our load is 500 milliampere. We considered headroom for more load or increased load or any unexpected behavior. 8.4 volt transformer is not available. We can select 9 volt, 10 volt, 12 volt. It is much better to purchase a transformer from shop instead of winding it at your end. Any transformer, if you are selecting 10 volt transformer, that's nice. Let's assume 10 volt transformer. $10 volt, 1 ampere, 220 volt, 50 hertz. This is the transformer value. If the voltage will drop 176 volt, 10 minus 10 multiplied by 2, 8 volt. That's excellent. Output at 20% line loss, that is 8 volt. 8 volt RMS. We can say 8 volt RMS transformer is good. We calculated 7 volt, but available transformer in the market will provide 8 volt. If you are selecting this one, If we will consider 9 volt transformer, that will provide around 7.2 volt. 9 volt transformer will provide 7.2 volt. Let's consider this one. We have 8 volt RMS 50 Hertz. When we will consider these 8 volt into peak voltage, RMS into peak, 8 multiply with 1.414, 11.312. V peak 11.3 volt peak. That is this peak. What will voltage here at this capacitor end? 11.3 volt minus 2 diode drop voltage, 1.4 volt, 9.9 volt peak. We can say our level here at this capacitor end, the peak will reach 9.9 volt. That is V peak high. And our allowed drop voltage here, dropped line 7 volt, that is the lower level for this regulator. What is the delta voltage change? 9 volt, that are high level voltage, minus 7, it is 2.9 volt. With the peaks here at 20% dropped line, variation will 2.9 volts. Now when we are calculating a capacitor, we need load current for charging and discharging into time. How much time will be allocated for charging and discharging, divided by delta V or ripple voltage variation, which we set this voltage. Upper level limit, lower level. We can say when we will connect it, this is our 7 volt line and this is 9 volt, 9.9 volt. Our peaks will like this after rectification. So this variation from this point to this point, 2.9 volts. When we apply any sine signal to a transformer, it provides output here, same frequency here and here. When we are using half wave rectifier, at that time the frequency remains same. But when we are using bridge rectifier, the output frequency is doubled. Why? Because this diode configuration provides 2-time switching. Output frequency of bridge rectifier is 2 Fin. 2 by 50, 100 Hertz. If you are providing 50 Hertz, output of bridge rectifier is this, that it clips negative peaks and provides in positive side. This is bridge rectifier. Now when we are connecting capacitor, this capacitor will work in 2 portions. In each cycle, in the rising time, it will charge when the voltage will start to decrease, because transformer's output is decreasing. At that time it will provide load current. In this portion, transformer will charge this capacitor and will drive this load. But when these voltage are dropping, because it is sinusoidal wave, when these voltage are dropped, it will start to decrease here. When the source voltage are decreased, then the battery voltage, that are capacitor voltage, it will stop charging. At that time it will become as a battery, it will provide load current. We have frequency 100 Hertz, that is output of bridge rectifier. This 100 Hertz frequency, one cycle, how much time? T is equal to 1 over F, 1 over 100. It is 0.2 millisecond. For charging and discharging, 10 millisecond. This 10 millisecond time is now allocated for charging and discharging. If we'll divide by 2, as we discussed, half portion for charging, half for discharging. So our time, charging time and discharging time will 0.005 second. We have current, the maximum current that this transformer can provide, it is 1 ampere. 1 ampere multiplied by 0.005 and voltage variation 2.9 volt, that is allowed voltage variation. 1 multiplied by 0.005 divided by 2.9, it is 0.001724 multiplied by 1000, it is 1.724 millifarad, but our capacitor always in microfarad. Again multiply with 1000, it is 1724 to 10 raised to power minus 6 or 1724 microfarad. This is calculated capacitor value. Remember that each capacitor has plus and minus. When we are considering capacitor, we must consider the negative tolerance. If the capacitor, original capacitor is 1724, might be it is less 20% or more than this. If that will less, that time that will not provide this capacitance. For that purpose we will increase capacitance value. C is equal to 1724 by 20% add plus 1724 plus 1724 multiply by 0.2, 20%, it is 2068. If we have capacitor with this value, calculated value with margin this one minus 20%, so this capacitor value will available all the time. But when we are selecting capacitor, we will not find this capacitor value exactly, so its upper level is 2200 microfarad plus minus 20% with low ESR value. Now when we are calculating capacitor, we need to check voltage. Here we calculated capacitance. We considered the voltage value with low voltage, but in case the line has swelling above than 220 volt, 20%, similarly the voltage will increase here at the output. We calculated this capacitor 10 volt at 220 volt. But if input voltage are swelled 20%, output will increase 20%. 10 plus 10 multiplied by 0.2, output voltage will 12 volt. (220) plus 220 multiplied by 0.2, at 264 volt. So our upper voltage value is 12 volt. Now check capacitor voltage. We say 12 volt RMS. Now we will say 12 volt convert into peak voltage 16.9 volt. We will consider 17 volt. The commercially available capacitors are 16 volt, 25 volt. So upper voltage value 25 volt. We will need capacitor 2200 microfarad at the rate 25 volts. This capacitor will work nicely. I hope this video is informative for you. If it is good, give a thumb up. If you have any question, please write in the comments. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.